in section 2, we're going to start taking a look at some basic geometric proofs. And just as we proved algebraic facts in section 1, we can also prove geometric facts about segments, angles, shapes, and a lot of other different things. And there are some geometric reasons we can use in proofs along with those algebraic ones we discussed in section 1. So one is the reflexive property of congruence. So if you have two segments being congruent or an angle being congruent to itself, that's reflexive. The definition of congruent, so if you have a segment congruent to another one, then their lengths are equal. Same thing for angles. If two angles are congruent, then their measures are equal. And those can go backwards as well. If the two measures are equal, they're also congruent. The symmetric property, which is similar to the symmetric property from section 1, you can reverse the order of congruence. The transitive property of congruence. So if we have a segment congruent to two different segments, so if AB is congruent to CD and if AB is congruent to EF, then EF and CD are also congruent to another. It also works for angles. If angle A is congruent to angle B, and if angle B is congruent to angle C, then angle A is also congruent to angle C. We have segment and angle addition. So if you have a point C between points A and B on a segment AB, then AC plus CB equals AB, so betweenness of points. It also works for angles. So if ray AB is between rays AC and AD in an angle CAD, then the measure of angle CAB equals the measure of angle BAD. We have segment and angle bisectors, which are just definitions we can use. So a line, segment, point, or ray that cuts a segment or angle into two congruent parts. We also have the definition of a midpoint, where the midpoint of a segment cuts the segment into two equal parts or two congruent parts. And we're going to use these along with the section 1 statements to help us with proofs. So the first thing we have is given the measure of angle 1 equals the measure of angle 2 and the measure of angle 2 equals the measure of angle 3, we want to prove angle 1, and this should say is congruent to angle 3. So our first statement says the measure of angle 1 equals the measure of angle 2 and the measure of angle 2 equals the measure of angle 3. Well, that was our given statement, so the reason for that is just going to be given. Next, we have the measure of angle 1 equals the measure of angle 3. Well, if we remember the transitive property, since angle 1 equals angle 2 and angle 2 equals angle 3, then by the transitive property, the measure of angle 1 equals the measure of angle 3. So this would be the transitive property. And then because the measure of angle 1 equals the measure of angle 3, we then have angle 1 is congruent to angle 3. And then our reason for that is that's the definition of congruence. So it's just as important to be able to make statements as it is to give the reasons for those. And sometimes making the statements is harder than giving the reasons because there's a lot of different ways you can approach a geometric proof to get to what you're trying to prove. Okay. Next, we're given the measure of angle A is 90 degrees and angle A is congruent to angle Z. We want to prove angle Z is a right angle. So first we have the measure of angle A equals 90 degrees and angle A is congruent to angle Z, which is what we were given, which is our reason. Next we have the measure of angle A equals the measure of angle Z. Well, if an angle is congruent to another angle, their measures are the same, which comes from the definition of congruence, so that would be our reason. Okay. Now that we know the measure of angle A equals the measure of angle Z, our next statement says the measure of angle Z equals 90 degrees. Well, we already knew the measure of angle A was 90 degrees, so using substitution, one of our statements from section 1, we can substitute that 90 degrees in for the measure of angle A. So we get our third statement by substitution. And then lastly, we have angle Z as a right angle. Well, since the measure of angle Z is 90 degrees, angle Z is a right angle, and the reason would be that's the definition of a right angle. So a reason, definition of right angle. So not every single one of these statements was from that first page. It doesn't have to be a statement that we're given that has to do with geometric proofs. Don't limit yourself just to those statements. We can use statements from section 1. We can use definitions that aren't listed there as well. So next, we're given that O is the midpoint of our segment NW and that NO is congruent to OC. And we want to prove that OC is congruent to OW. So we always start with what we're given. So one thing we're given is that O is the midpoint of NW. So its reason would be given. It is not the only statement we're given though as well. We see that the reason for our second statement is also given because we haven't listed the fact that NO is congruent to OC yet. So we have a second given statement. Next we have NO is congruent to OW. So if we label that in our picture, it might be easier to see. So NO is congruent to OW. Well, we were given that O is the midpoint of NW, and since the definition of midpoint is to split something into two equal parts, that statement being congruent comes from the definition of midpoint. Okay, and then our last statement, which is what we were trying to prove, says that segment OC is congruent to segment OW. We look at our second and third statements, we have that NO is congruent to two different segments. So by the transitive property, those two segments are congruent to one another. So our last statement that we were trying to prove, we get to that from the transitive property. And we have finished our proof because we've gotten to the statement we were trying to prove. So now in our last proof, we have two segments. We're given AB equals CD and that AE equals CF. So our segments are the same length, and then we have two segments on those that are also the same length. And we're trying to prove that EB is congruent to FD. So if we look at our proof, we have all of the statements getting us to our proof, but we need to fill out the reasons. Well, if I look at our first two statements, AB equals CD and AE equals CF, those were my two given statements, so their reasons are going to be given. Next, we have AE plus EB equals AB, which, if we look, E is between A and B, which means that statement comes from segment addition. And our next statement says CF plus FD equals CD. If we look at our second segment, F is between C and D, so that statement also comes from segment addition. Next, we have that AE plus EB equals CF plus FD. Well, from the very beginning, we knew that AB equaled CD. So I can substitute what CD equals for AB. So our fifth statement is going to come from substitution. Now in our sixth segment, we have AE plus EB equals AE plus FD. And we also have the statement that AE is equal to CF. So I can substitute AE in for CF in our statement from 5. So we get 6 by also doing substitution. Now that I look at my statement in 6, I notice that both sides have an AE. So if I were to subtract AE from both sides, I would end up with EB equals FD. So the reasoning for statement 7 would be our subtraction property. And our last statement, which is what we were trying to prove, says that EB is congruent to FD. Remember, definition of congruence, if two segments or angles are equal, then they are congruent. So our last reason would be the definition of congruence. Geometric proofs are a little bit more difficult than algebraic ones, because with algebraic proofs, you know what each statement should say to get to your what you're trying to prove, which is typically what x equals. With geometric ones, you start with what you're given and you know what you have to prove, but depending on what that is, there's a lot of different ways you can go about getting those statements that will end with what you're trying to prove. And our goal is to always use as little statements as possible. We don't want to have 19 statements where, 8 would have sufficed or even 4. So geometric proofs are harder than algebraic ones, but it's important to know the reasons to get from one to another and then start learning, okay, let's see what statements I can use to get to what I'm trying to prove. So when you're completing this assignment, please make sure you ask for help if you're not understanding where a statement came from or why that is the reason that would be used in that proof.